All right. So let's continue from where we were last time. So in the middle of this proof, we're about to prove something converges on a sequence of measures, converges to the par measure on S1 versus S1. So let's recall briefly the notion of weak star convergence. Weak star convergence. In a regular space X, let's call it some topological space. But what's a measure on X? Well, a measure on X just sort of assigns a number between a positive real number to any sort of definable subset of X, like any Borel set of X. So an open set, closed set, anything you can build out of that. And another way to think about that is a measure of X tells you how to integrate any continuous function in X with compact support to avoid issues of divergence and such. To integrate any F in sort of continuous functions of X, and the C here is for compact support. Okay, so you can literally think of it as a map from this to real numbers, such that any F that's just sort of non-negative gets a non-negative number out of this. Okay? And we say that a sequence of measures mu I converges from U under the weak star topology. It sort of converges in the weakest possible sense it could converge. Which is saying that for any fixed function f, the integral of f with respect to these measures converges to the integral of f with respect to u. Integral of f, so they call it integral of f of x with respect to the measure ui, yes, converges to the integral of f with respect to the measure u. Okay. Or another way to think of this is the weakest possible topology on the set of measures, such that all the functions integrate the measure with respect to f are continuous for every such function f. Okay. Every such f gives you sort of a map in space of measures with real numbers, and you want all of those.
Does it have to be like absolute value of f or anything? No.
Have to be non-negative, right?
Oh, we are.
No, f doesn't have to be non-negative. Sorry, am I missing something?
No.
So if you want to be a measure, it's not just any linear function. If you want to be a measure, usually you insist that if f is non-negative, then the integral is also non-negative. That's what it sort of means to be a measure. But this condition isn't any amplifiers or anything. Alright, and we say that mu is a probability measure. If the integral of 1 with respect to mu is equal to 1. Okay, so for a size function 1 measure 1. Technically, we're not always allowed to integrate 1 because X might not be a compact space. But you can sort of approximate 1 from below by bigger and bigger continuous function with compact support. And so you can still well define this, though sometimes it might be infinity for the real numbers or something. Okay. Okay, and so then a great thing about the weak star topology is that you have compactness of what's called the unit ball. So if you take any sequence of measures which give total measure x1, or something which is the most 1, then they have some limit. They converge to some other measure. So formally speaking, so if you let b1 of x be the space of measures mu, which the integral of 1 is less than or equal to 1, then b1 of x is compact under the weak star topology. Okay, so I'm going to prove this sort of fairly standard theorem in real analysis. Somehow the point is that the topology you're giving here is really the product topology, it's sort of the Diophantine topology, defined by all these various linear functions. Right, so you have a sequence of measures, you sort of pick a subsequence and they converge to the first f, and then the second f, and so on and so on. Okay. Any questions about this? Sort of a standard setup we use a lot, where we get some sequence of measures, and we take some big star limits. Okay, now if x is a smooth manifold, so if x, let's look at the space, so it also has some smooth structure on it, then in fact, if you look at compactly supported continuous functions, which are also infinitely differentiable, they're restricted to smooth functions, then this is dense. The space of all smooth functions with compact support under the supremum norm, or the L infinity. So in other words, given any continuous function with compact support, you can approximate it as well as you'd like by a continuous smooth function with compact support, meaning they differ. So, in other words, there exists for any IE, for any F here, there exists some G, with the supremum of F minus G on X being less than epsilon for all epsilon here. This is the way to quantify the problem. Okay? So in other words, if you want, what this basically says for us is if you want to show a sequence of measures converges, it's enough to test it on smooth continuous functions with compact support, which makes your life easier because these guys are much nicer than non-smooth functions, which we still sometimes have to deal with. All right. Now specifying x even more. So if x is just the unit circle or the circle, so let's just call x r mod 2 pi z. That's how we make up the circle. Then it's actually check that a sequence of measures converges to another measure. It's enough to show that all the Fourier coefficients converge. Integral chi of x mu I x converges to integral of chi of x mu x. For all characters, chi of x, chi of theta equals all the characters are, because I wrote it like this, you get all the data for some entity. Okay? So, there's sort of two ways to think of this. One is somehow easier and one is more hands-on. So the first way to think about this is the Stone-Weierstrass theorem. Okay, the Stone-Weierstrass theorem is a pretty general way to sort of use this kind of machinery. It says if you have any subalgebra, let me say, I think just from here, this is a subalgebra. Let's go in revision and multiplication. Then A is dense. If and only if A separates points. Okay, so clearly you need, for if this is dense, you certainly need for any 2 points in X a function which distinguishes between them. Otherwise, you'll never approximate any function which is like 1 at one point and 0 on the other. The theorem is that's enough. You have subalgebra which separates points, and the fact that it's dense is ECX, and so it's enough to check your measure converging on any of these guys. So one way to think of this is that if you look at the subalgebra generated by the characters, which happen to be closed in the multiplication, those certainly separate points. In fact, a single function, equal I theta, separates points. And so that sort of explains this fact here. Okay. This is all like somehow general nonsense, but it's worth understanding. Because it'll come up over and over again. Okay, the second way to think about this is somehow in terms of Fourier theory. Which often doesn't provide anything over just this fact, but sometimes you want more quantitative versions of this fact. So you can say the following: so if F is in sort of the compact function, let me say on armor to Z, let me say F of theta. Armor by Z. If you have some continuous function, I guess I don't need the compact support here, because this space is compact by itself. We can write A sub n as the nth Fourier coefficient of F. Right? And then because F is an L2, sort of by Fourier theory, what you can get from this, that if you integrate the square of F, it equals the square of the sum of the Fourier coefficients. Okay, this is true for any sort of continuous function on the circle, and it's sort of, this is true without it being true. You can expand F in the Fourier series everywhere. So it's a deeper fact for continuous functions. However, if F is differentiable, continuously differentiable, then, let me make sure I don't mess this up. You can actually get very strong bounds on the coefficients A sub n. Because if you integrate f prime of theta, you integrate by parts, so you integrate f and differentiate this guy. What you get is this is minus in times a sub n. Right? You differentiate the derivative of this guy is just minus in times this guy, so you get from there to there. Okay, and so as a result, you get that the sum over n and z of n to the power of 2 times an squared is equal to this guy, which in particular is less than infinity. Okay? And so what this tells you is that the sum converges. So you have some sort of decent value of the a sub n. So this is not quite enough to ensure uniform convergence, but if f is twice differentiable, then it is enough. So if f is in ck, what you learn is that the sum of n to the 2k squared over O(n) is less than infinity. And so in particular, if k is at least 2, and these a sub n are eventually less than 1 over n squared, and so you can sum them up and get uniform convergence. So if k is bigger than or equal to 2, you can actually write f of theta like this. This is the sum which converges sort of uniformly. And since the convergence is so strong, if you want to integrate f against any measure, you're sort of free to integrate these guys and sum up the result. Okay? And so, since we know that to check convergence of measure, it's enough to check them on smooth continuous function. Smooth functions are in particular C2, and so it's enough to check it on characters. Okay? So this isn't actually, I mean, for what we're going to use for today, this isn't that much stronger, but oftentimes if you're doing sort of more intense bounds, which we're going to do at some point, these sort of additional inequalities will be very useful. Okay. Any questions about this sort of, any of this character theory, Fourier theory, convergence stuff? Okay. So everything I've said for R1 2 by z for the circle also applies to like the circle to a power. So we're going to use it for the circle squared just now. Okay, let's recall the claim that we wanted. So the claim wrote down last time is that you have some sequence, the sequence of orbits under the Galois group of sort of pairs of points, each of which is a root of unity, which we can think of as just torsion points in C star squared. I should add the word distinct here. And we're going to assume something. We're going to assume that they don't sort of stay inside some fixed torsion concept. So such that for any character chi, so for any mn in Z squared not equal to 0, only finitely many, sorry, any of this and any root of unity theta, only finitely many of the SI, well, the points of AB in SI satisfy A to the m, B to the n equals zeta. So this is sort of, well, let me write it this way, actually. Let me write it this way. Only finitely many of these satisfy. No, that's fine, but let's keep it as this. Okay, so all these yellow orbits inside any orbit coset get only finitely many points. Then, if we let these delta SI, which we call are the measures assigned to this finite sequence of points, then these guys converge to the Haar measure on the even
So
circle.
there are fundamentally triples ABI.
Yes, that's right. So when you find many of these guys inside the union over all the insides. Yeah. So it's not easy to write. You can write it this way. Maybe another easier way to write it is you can just say A to the n, B to the n equals 1, in which case it doesn't depend which point you pick. It doesn't which point you pick, but it's low convoluted. No. We'll just keep it this way. Okay. All right. Okay, let's use the result of this proof. Let's show that all the Fourier coefficients, in particular the non-zero Fourier coefficients, the Fourier ones are kind of simple, converge the Fourier coefficients of these guys, of this measure, which are all zero. Right? Every character integrates to 0 and S1 equals 1, as long as it's not 0. So, let chi of Z1 and Z2 be Z1 to the n, Z to the n, for Mn positive integers, not both 0. So note that these characters chi, which are technically mapped from all of C star, on S1 cross S1 restrict to all the non-trivial characters. Right? So this guy restricts on sort of S1 cross S1, thought of as R mod 2 pi Z cross R mod 2 pi Z, to e to the in theta 1, in theta 1, plus in theta 2. Right? But it's kind of nice because we have sort of algebraic functions on the entire space, which restrict the set of characters we're interested in. So what we want to show is that the integral of chi of t with respect to the measure delta Si of t converges to 0. Right? So what you want to show is that if you take this character chi and you sum it along all the points in Si, and you average, then that goes to 0. Chi goes to infinity. That will sort of show for the test function chi that we get convergence when we want. Okay, but what is this guy? Sort of this integral of chi of t dSit, again, just unpacking it, is the sum over T in Si chi of T, where the sort of prime means you divide the number of elements in the sum, so you get sort of the average number. And the point is that chi, this map chi is defined over Q, so it commutes with the Galois action. Remember, Si is a single Galois orbit, right? And so you can also write this as a sum over, we call it like T prime in chi of Si being now a Galois orbit inside Q bar star, Q bar, of T prime. Again, average. Right? Which I can think of, if you're writing it again in this language, as the integral of the function sort of z, or the function t, with respect to delta Si of t, delta chi of Si of t. Okay? So I'm just sort of pushing around notation right now. We're not actually doing all that much. But what actually happened here, the point is we're summing over these guys Si, over these orbits, the character chi. And the way to rephrase that is you can first apply chi, you get some Galois orbit inside Q bar, and then sort of sum, this is the function of t, the sum of those guys. So nothing really has changed. So it's sort of a useful trick because we've now in effect reduced ourselves to the one-dimensional case, what we're trying to show. So chi of Si, note, is a Galois orbit inside not just Q bar or C star, but in fact the stores in something. If you take any pair of numbers, each of which is a root of unity, and you apply this character, you get another root of unity. Right? So now the sequence chi of Si is just a sequence of Galois orbits of roots of unity. And moreover, by our assumption, the sequence isn't quite all distinct. You can have repetitions, but only sort of finitely many times on the whole basis. So by assumption, every orbit occurs at most finitely many, well, I guess finitely many times, possibly zero. Inside chi of Si. Right? Otherwise, you have a solution to chi of some number is equal to some fixed root of unity, and we started out by assuming that doesn't happen infinitely often. Okay, so you have some Galois orbits of roots of unity, which are doesn't stay fixed, they keep changing, and we have to show that they become equidistributed with respect to our measure, or even weaker, that if you just average all of them, you get something which goes to zero. Okay? So we're now purely reduced to a question about roots of unity. In particular, the character chi has sort of gone out the window. Okay? And it's sort of short if you think about it, because one character chi is really different than any other character. You can apply an automorphism of C star squared to sort of take any primitive character and any other character, and so proving it for one guy should be the same as proving it for all of them. Any questions about this sort of step before we finish it? Sorry if I'm being pedantic or very fast. Either of them. I'm sorry. Okay. So let's prove this. So there's a sort of nice fact that you can describe the Galois orbits of the roots of unity very explicitly. It's sort of as simple as it can be over Q. And this is mainly the reason why we restricted to Q to begin with. You can make this argument over any number field, but over Q it's an extra level of explicit. So the roots of unity we can write as a union over all positive integers of the nth root of unity. That's not too difficult. So this clearly isn't a Galois orbit because, for example, the order of root of unity is preserved on a Galois homomorphism. That's not hard to see. So you can write it as this joint union over the primitive roots of unity. So these are exactly the integers x, or not the integers, the numbers x and c star, y star, such that so the precise multiplicative order of x is equal to n. The nth power is 1 and the smaller power is 1. And so a sort of fun fact, which you prove in algebraic number theory, you can prove it without that, using Galois theory in finite field, is that this is a single Galois orbit. Okay, so the Galois orbits of roots of unity are precisely taken integer n and look at all primitive nth roots of unity. Okay, so once we have this, the proof isn't that hard to finish. So remember, what you want to do is understand the average, let's say the sum, over primitive nth roots of unity. And so here we use exclusion principle. So we sum over all d divides n, d squared free, minus 1 to d, sum over all t, and n over d through the unity of t. Okay, so this is like that. Application of inclusion exclusion. All that gets preserved in the sum of the primitive root of unity. And now what is the sum over all t in here? Well, this is the group, so you can show the sum is 0 unless there's only one term in the sum, which is 1. So this is equal to 0 if n is not square free. Sorry, this is minus 1 to the number of prime factors in d. U of d, not to the d. My apologies. And otherwise, it's minus 1. I'm sorry?
You just mean mu of d, not negative 1 mu of d?
Oh,
Or so
yes.
mu of d. Or
Yes.
omega d.
I mean-
Omega. That means smaller.
Yeah, I mean mu of d. Yes, because I've confused everybody, including myself. Recall that mu of d is just minus 1. So the omega d, so omega d is the number of prime factors of distinct prime factors. Sorry. That is all I need. Is it right now?
Your definition of mu is true of d is square root.
Yeah, right. You these are free. Which is all I needed for you. So these are free and well, yeah. Otherwise, you use 0. But let's not worry about that right now. Okay, and so it's this and mu of d otherwise. Mu of d and this square root. Okay. Anyways, the sum is either 0, 1, or minus 1. Now the size of the primitive roots of unity, this is the order phi function, n, which goes to infinity pretty quickly. And so, if you look at the average size of these guys, you average out, and this thing you sort of at most end up with value 1 over phi of n. It goes to 0 and then goes to infinity, like pretty quickly. Yeah, it grows larger than the power of n, bigger than 1. Okay? Did I make a mistake somewhere? I'm getting some funny looks.
Shouldn't you then, I think, not that.
I'm sorry? You have. Thank you. Anything else? What is that? Is that it? Okay. Okay, so once again, what have we done? We wanted to check that for any character chi, the integral, the sort of integral of chi against our measures delta Si convert to 0. We reduce it to checking that roots of unity, you sum them up, you get something, an average, get closer and closer to 0, and we can just explicitly check that over here. Okay?
Wait, what? Only, like if n is a, if you're just going over n primes, for instance, then phi of n does not go to
5n t minus 1?
sorry.
Okay. So, what do we know? We know that, going back to what we're doing, that chi is not the identity character. Then the integral of chi of phi with respect to these guys converges to 0. And if chi is the identity character, then the integral is 1 with respect to these guys. All the probability measures, these numbers are all 1, and so the limit is 1. And so therefore, these guys do in fact converge under the weak star topology to US1 plus 1. Okay? Alright. So that proves this claim. Let's recall how that relates to Lang's conjecture. So we have some subvariety V inside C star squared, not containing any torsion coset. Right, and we assumed that V intersect these guys is infinite, and reduce the case where V is defined over Q. Okay? So then by this result, so by star, if you let S of I be the Gauss orbits of V intersect the retrievability. And because V doesn't contain Victorian coset, our assumption is satisfied, and so these measures converge to mu S1 cross S1. And the reason that's ludicrous is because if you intersect V with S1 cross S1, that's a closed subset, and that sort of can't happen. So if that can't happen, you can take any function f, S1 cross S1, which is sort of non-negative, and supported outside V, intersect S1 cross S1. Right? Then on the one hand, the integral of f against these guys should converge to the integral of f. On the other hand, the integral of f against these guys is plainly 0. Because these guys all lie in V, and f is defined to be 0 on V, intersect S1 cross S1. And that's a contradiction. Okay? Okay, that wraps up the proof of the first case of Lang's theorem. So, let me sort of make a comment about this proof, which is that it is in fact an effective proof, even though I didn't state it that way. Right? So we phrase it in terms of the language of sort of measures converging to each other. And if you think about it, you have sort of an actual V that I'm sort of giving you with equations defined over Q. Well, what I can do is I can take an f. Sorry, let me put an infinity here to make the argument easier. It doesn't extra. I can sort of write down an explicit f. Once I sort of have some brackets writing down the function in general, I can write down an explicit f from S1 cross S1, which is 0 on this closed set. To sort of find the little open ball, make my favorite smooth convective support function there. I can expand it out in terms of its Fourier coefficients. Right? I can pick a big enough n such that those averages I was talking about get really quite small, and I can make my contradiction sort of infinite time. So let me just spell that out, because I think it's worth sort of understanding how this can be effectivized. So, to effectivize, so what you do is first you find f, find or make, which is 0 on V, intersect S1 cross S1. That's the first step. The second step, you sort of write this down. And like this. And now we know, sort of by abstract theory, that these guys go to 0 very quickly, faster than any power of n. And so in particular, I know that after a while, the later bunch of Fourier coefficients are all like really quite small. And so then what I do is I find, sorry, there should be two functions, right? This is in1 theta 1 plus in2 theta 2, and 1 and 2 in z squared, in1 comma 2. Sorry about that. Yeah, so f exists on sort of Fourier expansion has two variables in it. Okay, and so we're going to take f to be non-negative, so a0, 0 in particular, fully positive. So find like r bigger than 0, such that if you sum up all the Fourier coefficients for one of these guys is bigger than r, or some is bigger than r or something, then this sum is really quite small, less than a00 over 2, say. Okay. So you can sort of do all this. You know, you can't actually write down infinite sums and stuff, but if you find that explicitly enough, then you can actually find this number R, that this is true. So let me maybe erase some of this. So this. Okay, now by assumption, if Si is one of these yellow orbits, so it's in V intersect this set here, we know that the integral of F with respect to this is equal to 0. Right? We know that this is true. On the other hand, by sort of L2 theory, this is equal to the sum over n1 and n2 in z squared of the Fourier coefficient of F times the n1 and n2 Fourier coefficient of this set here. This is Fourier theory. Times the integral over S1 cross S1 of E of minus N1 theta 1 minus N2 theta 2 delta Si of theta 1 theta 2. Right? So we can explicitly write 0 is equal to this thing over here. Now each of these terms is at most 1, and we know that these terms, after a while, become really quite small. So as long as we can make all the first bunch of non-zero terms small enough, we get a contradiction. So the fourth step is pick M such that the sum over pairs of numbers which are at most R and not both is 0 of A and 1 and 2 times this thing times this thing. If we can pick an M such that this sum is at most A00 over 2 for SI, so M torsion points, so a torsion point of order M, then we're done, right? Because then we know that this intersection can't contain torsion points of order, at least M, greater than M points. A better way to say it is like torsion points of order at least M. Then we've concluded that you don't contain any torsion point of order at least M. And all you got to do is pick a torsion point of order most M. That's a finite set. You can go and check them all. And so you found all the torsion points inside Q. Right, so all we got to do is find a big enough M, which makes these guys small enough such that the sum is as small. But we can do that because these guys are roughly of size 1 over phi, as we know, and 1 over phi goes to 0 pretty quickly in effect. So we just somehow pick a big enough M where this is true, and then we're done. Okay, so this is a sketch, but this is sort of how you would make this kind of argument effective. So it's another reason why you sort of often want to use Fourier theory in terms of just a Distil-Marchas theorem. Allows you to give like actual bounds on things and give actual effective arguments instead of abstract principles that are very hard to do this from. Any questions about this? Or rather fast sketch. Okay. Oh, I see. Okay, so the next thing we'll do is we'll talk about what Lang's theorem can say for us in higher dimensions. It turns out there's sort of two different ways to generalize it, and one of them might not be stronger. So we'll sort of explain that. Our proof will basically carry over, and then we'll move on to some other stuff with heights. All right.